Section 5.1, Energy and Energy Changes. So thus far in our study of chapters 3 and 4 of chemistry, we've talked about matter, we've talked about changes in matter. Now we're going to start talking about energy. So let's begin by thinking about what is energy. There's not a really perfect definition of energy, but energy is often referred to the capacity to perform work. Now, in a sense, that definition is somewhat circular because it turns out work is a form of energy. But let's try to be practical about this. The whole concept of what we're talking about here in terms of energy is a very practical science. It has to do with how we make things like automobiles and aircraft and steam engines and batteries. We're really talking very practically now. So imagine that we have a cliff and we have a box, and that box has mass, and we want to move that box up to the top of that cliff. What we would claim is that it requires energy to perform that task. Okay? There's something about matter that is required to be able to do this. Turns out the mass can't just spontaneously hop up to the top of the cliff. Likewise, if we have a flat surface and we have some sort of vehicle, like a bus, and we want to drive that vehicle to the next city, we recognize that there is a requirement of energy, right? Energy is required for that to occur. The process of moving the mass up to the top of the cliff or moving the bus 10 miles to the next city, that requires work, and work is a form of energy. Now, we recognize with the bus that this could be done by using an internal combustion engine, which uses gasoline, right? And that gasoline is a fuel. And so there is energy content within that fuel. It turns out matter has energy. So now let's consider a couple of processes that might occur. One is the melting of ice into liquid water. Right? That's not a chemical process, it's a physical process, right? There's no chemical change in ice to water, even though they seem very different. Ice cubes will float on liquid water, so they have a different density. Ice cubes, if they have air molecules trapped in them, will be cloudy, so you can't really see it through it. Pure water is pretty transparent. One's a liquid, one's a solid. They're very different materials, seemingly. But they're the same chemical process, right? If we put the liquid water back into a freezer, it would turn right back into ice cube, and it still has the same chemical composition. For every 16 grams of oxygen, there are 2 grams of hydrogen. So it's the same substance. That's a physical process. It turns out it takes energy for this to occur. Energy is required to melt ice into liquid water. Likewise, if we consider a chemical change, such as hydrogen and oxygen reacting to form water, this releases energy. into what are called the surroundings. And that's an important term in this discussion. The surroundings is the space around the process that you're studying. So for example, if I have a coffee cup and I have an ice cube in here, the ice cube will convert into liquid water. It starts melting, right? You've seen this happen. It starts melting into liquid water till it disappears. The reason for that is that energy is being transferred into the coffee cup from the surroundings. The source of the energy is the surroundings, the space around that coffee cup. Likewise, if we run a reaction, here's an example of how this reaction could be run, the chemical reaction. We could have a big tank full of hydrogen gas. We could have a separate tank full of oxygen gas. We could then pump those two gases into a reaction chamber and put a little spark plug, a little bit of electricity. And as those gases mix with the input of energy from the spark plug, they will react and form liquid water. First it'll convert it into gaseous water, which then will become liquid water as it cools, and you have a reaction occurring. It turns out that energy is released by that process. And it'll come out in different forms. It'll come out in the form of what's called heat, which we'll talk in detail about. It'll come out in the form of light. You'll see light, it'll glow. And so energy is being released to where? To the surroundings. Energy is being released to the surroundings, okay? The space around the area that we're studying. So we're studying that chemical reaction around there. Energy is going to be released. Okay, so let's talk a little bit about terminology. The rest of this section is just terminology. The first one is kinetic energy. This is a way of thinking about energy. Kinetic energy is a type of energy. It is the energy of moving particles. So if an object is moving, if a particle is moving, we claim that it has motional energy. Instead of calling it motional energy, we call it kinetic energy. It's a cooler term. It turns out that if you have a particle that has mass and it is moving, you can calculate its kinetic energy very simply. The kinetic energy, E sub k, this is the notation your textbook uses, of that moving particle is 1/2 times the mass of that particle times the speed of the particle squared. Okay? The speed or velocity, I don't particularly like the symbol U for velocity. I like the symbol V, but your textbook uses a U, so we'll stay with that. M is the mass, right? That's the amount of material you have. So 1/2 times the mass of the particle or the object times the speed or velocity, if you want to use that term, squared would be the amount of kinetic energy that that particle has. Okay? And it turns out there's a type of energy in chemistry that we use quite a bit called thermal energy, which is a form of kinetic energy. It turns out if you consider a gas, we'll talk more about this in chapter 10. A gas, a sample of gas, is a bunch of particles, tiny particles. Actually, let me draw them a little smaller here, that are moving around. And I'll use arrows to indicate the direction that they're moving and the length of the arrow to how fast they're moving. So a gas is a collection of large number of particles moving randomly in different directions at different speeds. Each of those particles that's moving has kinetic energy, right? Because each particle has a mass. For example, an oxygen molecule has mass. If it's moving at 100 miles an hour or 500 miles an hour, it has a velocity, it has a speed. So it would have a kinetic energy. So each of those particles would have a kinetic energy. Okay? Now let's talk a little bit about some other forms of energy. One type of energy is called potential energy. This is the energy of a particle due to its position. Interesting, right? Turns out that relationships between objects or particles can correspond to energies. And so if the position of a particle changes, its potential energy changes. An example of this would be a staircase. So here's our floor. Here's the top. If we have a ball at the top, what we would observe is that if you pushed it just a little bit to the right, it would start bouncing down the stairs, and by the time it hit the floor, it might be moving pretty quickly. On the other hand, if we take that same ball and we move it over here, and we move it a little bit to the right, just give it a little shove to the right, when it hit the floor, it would be moving, right? And it would be rolling, but it wouldn't be rolling as fast as this one was when it hit the ground. So if this one, came down all the way here, it'd be moving pretty quickly, perhaps. So it'd be high speed, at least higher speed. And this one here, it'd be slower. And that's because the object at the top has more potential energy than the one that's down here, okay? Assuming their masses are the same and you're pushing with the same forces. So somehow the position of that ball or that marble, whatever it is, its position corresponds to how much energy it has, or at least it affects how much energy it has. So that's called potential energy. That's gravitational potential energy. There are other forms of potential energy. There's what's called electrostatic potential energy. This one's important for us because chemistry is related, a lot of chemistry is related to the structure of the atom, or structures of molecules. Atoms have protons, atoms have electrons, those are charged particles. So for example, if I take an electron, and I'll represent the electron using a little ball with an E negative, and then I take a proton and I put it over here, so here's our protons, positively charged. The sizes of those little balls have no relevance to anything here. They're just showing that these are separate particles. It turns out there is an attraction between those two particles, and that attraction has an energy. Okay, there's an energy of attraction, and that's called electrostatic attraction. We would say that those two particles have electrostatic potential energy. It's attraction because if particles have opposite charges, they undergo attraction. Oops. If they have the same signs, it's repulsion. So what we would claim is that if we had two electrons the same distance away from each other as the electron and the proton, there would still be an energy but it would be an energy of repulsion. Okay, so this comes up quite a bit when we're discussing the structures of atoms, the structures of molecules. The fact that atoms and molecules are constructed of particles that have charges, that's going to result in potential energy, electrostatic potential energy. The electrostatic potential energy, we'll call it EEL for electrostatic, is proportional, not equal to, but proportional to Q1, which is the charge, the electrical charge of the first particle, times the electrical charge of the second particle, divided by the distance between them. So Q1 would be the charge of the electron, -1. Q2 would be the charge of the second particle, -1 in this case. And then D would be the distance between them. So notice it's a ratio. Notice it's also not an equality. Your textbook does not show this as an equality. In physics, you would learn this as an equality, meaning we would put a constant in front of the right side of the equation of the proportionality, and that would turn it into a equation, which is called Coulomb's law. So I'll just show that for you here. This is called Coulomb's law. Okay, so electrostatics. So it turns out that charged particles also have energy in relation to each other. Now, another aspect of chemical reactions has to do with what we call thermochemistry. So we're going to be talking about thermochemistry in this chapter. And so thermochemistry is related to heat changes or heat transfers in chemical processes. Okay, so thermochemistry is the study of heat transfers in chemical processes. It turns out that if we run a reaction, a chemical reaction, in a container, sometimes that reaction releases thermal energy to the surroundings. So this is the surroundings. And if thermal energy is transferred to the surroundings, we call that heat transfer. Thermal energy transfer is called heat transfer. We call that an exothermic process. For those of you that are familiar with the anatomy of certain types of creatures like insects, there are skeletons that are called exoskeletons, right? That means the skeleton's on the outside of the body. So exo in this context means outside. So energy, heat, is being transferred to the outside of the reaction, okay? It's going out to the surroundings. That's called exothermic. Now, the opposite process would be that your chemical reaction in the coffee mug, when it occurs, heat is transferred into it. This is called an endothermic process. So if heat is being transferred into, then that's endothermic, okay? Those are less common types of processes. Think of a rocket, right? Or an explosion. These are what we would call exothermic processes, meaning you can see, wow, energy is definitely going out into the surroundings. You can see what happens outside of the rocket or outside of the explosion. Endothermic processes are less common. You don't see those very often. One example of that are those ice packs. You ever seen those? You can buy them pretty cheaply. It's often meant for injuries, that if someone like hurts themselves and you want to cool off the injury. It's a gel in a pack, and then you twist it, and then it turns into a solid, it looks like ice. And it's cold, right? It feels really cold. It's a cold pack. Well, those cold packs, what's happening is a chemical or physical process is occurring, and it's absorbing energy from the surroundings. Well, you're the surroundings. Your leg is the surroundings. So to your leg, it feels cold, right? So endothermic processes for us, they feel cold. Whereas exothermic processes, they feel hot. There's hot packs too, right? Hot packs, they release thermal energy. They transfer heat to the surroundings. And again, your hands would be the surroundings. Okay? So endothermic, heat goes in. Exothermic, heat goes out. Now let's talk a little bit about units. There's a discussion in here about units. The SI unit for energy is called the joule. And the abbreviation for the joule is most commonly a capital J, although sometimes I've seen it as a little j. And the joule, 1 joule, is equal to 1 kilogram meters squared per second squared. That's a joule. Okay? So really what that means is, if we kind of think about an example of this, would be that if you picked up a pencil and you took that pencil and you moved it up about a meter, that would require about a joule of energy to do that. Okay, it might be 1 joule, it might be 2 joules, but it's around a joule. Now for chemical calculations, the joule is often a little too small for us. So we also use what's called the kilojoule. So a kilojoule is 1,000 joules. Right, the metric prefix K is kilo, so that's 1,000 joules. All right, so the kilojoule is used more commonly in chemistry. Okay, so I'm going to show you for this, let me just show you a quick calculation involving units and numbers. So let's imagine this. So here's an example. Let's imagine that we take our textbook. Now you're using an eBook probably, but right next to me as I talk to you, I have a physical copy of the textbook. And the mass of the textbook is actually about 1 kilogram. It's around 2 pounds. It's about 2.2 pounds or so, so it's 1 kilogram. 1 pound is, I'm sorry, let me put it this way. 1 kilogram is 2.2046 pounds. So about 2 pounds is what this textbook weighs, okay? So now what I'm going to do is I'm going to move it. I'm going to push it across the table. Let's assume the table doesn't have any friction. And I'm going to move it 1 meter a second. So imagine this book sliding across the table at 1 meter per second. Remember, 1 meter is about 1 yard, right? So that means it's moving pretty quickly, actually. It's moving on the table an entire meter in 1 second. That's how fast it's moving. Let's calculate the kinetic energy of that book. right? 1/2 mu squared. Okay, well, that would be 1/2 times the mass, 1 kilogram, times the velocity squared. So you can see why I picked those numbers. 1/2 times 1 squared is 1/2, right? 0.5. And the units would be kilogram meters squared per second squared, right? Kilogram is the unit of mass. The unit of speed is meters per second. You guys square that, so it's meters squared. So in other words, 0.5 kilogram meters squared per second. Well, that's half a joule, right? It's 0.5 joules because 1 joule is a kilogram meter squared per second squared. So the kinetic energy of that book, as it moves across the table at about a yard, a meter every second, would be about 1/2 joule, 0.5 joules. Let's be a decimal number. And then how many kilojoules would that be? Well, 1 kilojoule is 1,000 joules. So if we wanted to convert that to kilojoules, I would take 1/2 joule and then say, hey, 1 kilojoule is 1,000 joules. So if you do that, you get 0.5 times 10 to the minus 3 joules. So that's kilojoules. Joules cancel. So that's not very many kilojoules, right? Well, it turns out chemical reactions produce quite a bit of energy often. So kilojoules is what we'll use for those. But for this moving book, that's how much energy it would have. Okay? So you definitely want to try the sample problem 5.1. I'll show that in a separate video and do the checkpoints as well in the practice problem A and B.